Good afternoon or evening. Hopefully it's not 3 a.m. that you're looking at this. We're going to look at differential equations, and our job is to know and understand what are differential equations, and we're going to look at some solutions to differential equations. And the type of differential equations we're interested in solving at this point in time are first order differential equations and second order differential equations. They're going to be linear. They're going to be non-homogeneous differential equations. So that means that we're having a function of x on the right hand side, not a zero. And they are, of course, our ordinary differential equations we're looking at. Please note these are the exercises I'd like you to be working on from 9b and 9a and 9b. We're going to focus on work pertaining to exercise 9b, which is the first lot of strategies to solve these types of differential equations. And then in class we might look at a few problems pertaining to exam problems, but we're going to move ahead and look at the next type of differential equation in class. So let's explore what we can get from the strategies we will learn for solving differential equations. Okay, we've got these two types. Let's see if we can name them, try and describe them and categorize them. This is not 100% crucial part for your learning, but it's good to, I'd like to be able to say, put a name to this. Mr. Homogeneous, for instance, because, just calling it that thing is not nice. When you study maths at uni, hopefully everyone studies at least some maths at uni, you're going to come across these guys again, and you'll definitely be using these terms, so it'd be good that you've been introduced to them and you start to use them a little bit. I have this one here. What would we say? Is that first order or second order? Look at the highest power of the derivative. It will be second order dE. And it is linear because the dependent variable is linear. If that was another y term in here, a dependent variable term in there, if that was a squared or a e to the power of y, then it will be nonlinear. It's also non-homogeneous because we have a function of x on the right hand side, not a zero. What about this one? This is first order because it's the first derivative, and it's linear because the dependent variable is just linear term, and it's non-homogeneous also. Okay, so that's the type that we're going to learn the strategies first for in the beginning. This is a famous differential equation that matches these forms. Okay, Newton's second law, an applied force on an object is given by the product of its mass and its acceleration. Mass times acceleration is force. Okay, but this doesn't seem like a differential equation, except acceleration, we can write it in terms of dv dt, or the second derivative, dx dt. X is your displacement, okay, and v is velocity. Very important concepts that we're going to be exploring when we look at kinematics and vector functions. So let's see why this is the case. I've got, if I just transpose this for A, I'll have A equals F over m, and then using this definition, acceleration is first derivative of velocity. dv dt equals F over m. And let's say for some object, constant force is applied to an object, and the object has a mass which doesn't change, so this is just some constant number. This is a constant. Okay, this here fits perfectly with this type of differential equation, where our function of x here is not actually a function of x, but it's a constant, which fits under the category of some function of x. This can be anything, arbitrary. Okay, anything at all. Well, we've also got from here, we've got the second order dE form as well. So acceleration could also be the second derivative of displacement with respect to time, and again that's equal to a constant. Alright, now this is this form, precisely. Second order, it's linear and it's non-homogeneous. Alright, so this differential equation, these two, we'll be looking at in more depth very shortly in this course. Let's look at solutions to differential equations. So start with the basics. This is the first one we're going to solve. Now you can approach this intuitively, not just blindly applying a method, but it's important to understand the procedure of the method because it's something we apply across the board for all types of differential equations. So you can think, well, if the rate of change is x, then the function y as a function of x has to be like the antiderivative. If the gradient is x, then the original function has to be like an x squared, or more precisely half x squared. Because if I go ahead and differentiate this, I will have half x squared. I will have x, simply. But I have to be careful with doing anti-differentiation and integration is that I can't forget my plus c. We've got to always remember that. Now, with this method, we're going to make a few assumptions and just establish some basic facts about integration. This is an important concept here. This is saying the integral of dy is y. Okay? dy is a little small part, just a little y. Alright? Y is broken up into little parts. The integral is your infinite sum. So what we're doing, we're summing up all the small parts of y. All the small parts of y are your dy's, and to have a whole amount. We're joining them all together to get the full y. And that's what integration is all about. We're integrating, bringing together all the little bits to form a whole. So if we can understand that, that's the first bit. Then also we're going to draw on this little skill, this little idea. It's a shortcut thing. We want to treat our dy dx, our gradient, which is the derivative operator, we want to treat that as being a fraction. Work with it as a fraction. Okay? So that means fractions have a numerator, denominator, and we can split it up. We can divide by the denominator to remove it and so on. We're going to separate the dy's and the dx's, which is kind of, not mathematically legal, but, let's throw all the rules out the window. We can do that. Why not? As long as it works for us, let's do it. Let's take this one. So what we're going to do, I'm going to multiply both sides by dx. Because it's a fraction now. A fraction. So I'll have dy equals to x times dx. Now this is a small little bit of y. I want a big y. So I'm going to integrate dy to get y. But this is an equation I have to remember. And what I do to the left-hand side, I also have to do to the right-hand side. So if I go ahead and integrate on the left, or I have to integrate on the right as well. So this basically gives me, the integral of dy is y, and now I've got an integral of x with respect to x. So that is my half x squared plus c. And there's my solution. This is the general solution. Okay, because it could be anything depending on what c is. C could equal to 1, c equal to 2, c equal to 3. Lots of different solutions. Okay? Let's have a look at some slightly more complicated ones. And here I've outlined the steps of the method. So step 1 of the method, we have to separate variables to either side of the equal sign. Okay? So it kind of makes sense with solving equations. With a linear equation, we put the pronumerals to one side and the constants to the other, all the numbers to the other, to get a solution for x. This time we want to put the y, the dependent variable, on the left, and the x, the independent variable, on the right. We also have to do the same with the dx's. We have to split it up. So we're going to put the dy's to the left and the dx's to the right. Let's try it. Let's go through those steps for the first one. X to the power of 4 minus 3x squared plus 2. So right now we've got just the dy by itself on the left. That's good, nice and convenient. We've got all the x terms on the right, but we've got the dx down here. So I need to multiply my dx onto the right hand side, and I'll have dy equals to x to the 4 minus 3x squared plus 2 dx. Don't forget to include the brackets. Okay? So now, this dx returns back to being an operator for integration. So I'm going to integrate both sides, the left-hand side and the right-hand side, integrating both sides of the equation, step 2. Okay? So I integrate all my little dy's and I get y. And now I've got a function of x, and when I integrate my function of x with respect to x, alright, I'll have my result, my integral. So I'll have x to the power of 5 on 5 minus x to the power of 3x to the power of 3 on 3, and the 3's cancel. That's good. Plus 2x. Now, have I forgotten something? Got to not forget my c, my plus c. Fortunately for this example, step 3 is done. Transposed for the dependent variable y. This is an important part which is going to come into play later on. Must remember that step 4 as well. Plus c, very, very important. Okay. Easy. Let's have a look at 2. So, for this function, dx dt equals to e to the minus 3t plus 1 over t. Now, we don't have x and y's. We've got x is now a dependent variable, and t is our independent variable. So we're integrating with respect to t in this case. So, go through the steps. Got to collect all the terms. Dx is on one side, and x terms on the other side, and t is on this side. So I'm going to multiply my dt to the other side. I'll have e to the minus 3t plus 1 over t dt. Now let's integrate both sides of the equal sign. So the integral of dx is just x. And now I integrate each part separately. So that will be negative a third e to the negative 3t. And the integral of 1 over t is, who can tell me? Taylor? What is it? Very good. It is log of t. Don't forget the modulus. And finally, what's one thing we have to remember? Chi, what is it? Plus C. That's it. And there we have solution to solve the solution for differential equations. Who can tell me what kind of solutions these are? Monique, what is it? It's a general solution. That's right. We've got general solutions here. General solutions, because it's not a particular solution. We need our conditions, our initial conditions, to work out what the C values are. All right. Now another little some terminology we can use to describe these general solutions is called a family of curves. Family of curves is something that a function that all have the same gradient, such as this situation where we have a function y equals a half e to the 2x plus 1. Okay? Or y equals a half e to the 2x. Y equals a half e to the 2x minus 1. They all have the same gradient, the same curvature. The only thing that's different is the constant at the end, where this one is plus 0. Alright? Let's see how that applies to our differential equations. It says find the family of curves whose gradient is e to the 2x. So whose gradient is e to the 2x. I've got, let's consider y to be e to the 2x. So then we're told that, being the gradient of y, which is dy dx, is e to the 2x. So that means I can work out what y is through solving my differential equation. Integrating both sides. Y equals a half e to the 2x plus c. Okay, and that's the significance of this plus c, because it produces any curve, any graph we have here and more. But every single one of this, they all have the same gradient. So we say that this here is what we call a family of curves. General solution is a family of curves. Let's look at the next type. Differential equations of the form like this. It's a second order ODE. Now, approaching this one, we have to employ a little substitution. Okay? It basically says, well, I know how to solve a first order differential equation that looks like this. I can solve a first order one, so I'm going to make it a first order. I'm going to let P or any other pronumeral like a U or something different than what we already have given in the problem. I'm going to let P is equal to one derivative, dy dx. So then this now becomes dp dx is equal to the function of x. Okay? So let's try that in this example. So first, being a second order, I have to substitute and make it a first order differential equation. Let p equals dy dx. Okay? Now the second derivative is basically differentiating dy dx, which is p. So I set up a new problem. First order derivative, differential equation. Now I can go ahead and solve it. So dp is equal to cos of 3x dx. Integrate on both sides. The right hand side becomes p is equal to now the integral of cos. Well, I know the derivative of sine is cos. And so the derivative of cos is minus sine, so the integral of cos is positive sine. With the third out the front. If I just leave it like that, I'm forgetting something very important. I'm forgetting my plus c. Okay? Now this part is crucial more than ever, because now my plus c is a constant in the rule, and it's going to take part in the next stage that's going to happen. Since I made this substitution at the start, I have to bring this back in. Alright? Now let's sub p is equal to dy dx back into the rule. And I'll have dy dx is equal to a third sine of 3x plus c. And we've got a second problem. It's another one of these. Okay, so solving a second order differential equation is like solving two first order differential equations. So I'm going to integrate dy on both sides. Plus c with respect to x. Okay, I know this straight away becomes y. Now, let's go ahead and integrate. I've got two parts to integrate now. What's the integral of sine? What is it? Minus. Very good. Minus cos. So I'll have a negative ninth cos of 3x. Good. And then plus c. But that's, we have to remember, like a number, like 1 or 2. Okay? So the integral of a constant becomes an x term. This is now a c times x. It's very important now. It's now a function of x that takes part in the general rule. And we're done? Is there anything else you think? Well, when we integrate the first time, we have to include the integration constant, the plus c. When we integrate the second time, we also must include an integration constant. It's just part of that process. So we'll have another one, another constant, plus d. Okay, and then if we have a third process, if this was a third order differential equation, we have to do the same thing again. We have to integrate a third time, and we'll have another integrating constant called plus e, and so on. And we've got our general solution. So I hope this makes a bit of sense, and that we can see the pattern, what goes about, and how to approach these types of differential equations. Let's now consider some more important problems, some interesting problems here. Let's look at what happens if we want a particular solution. Particular solution is one unique solution where we have to use a little bit of extra information to substitute and work out what those constants are. Now, what I'd like you to do, please check this one out. Page 346, exercise 8. Please work through that and write it into your workbook. It's a very useful example that I'd like you to study. So from 9b exercise set, question 4, find the solution for the following differential equations. Here's my differential equation, and here's some extra bit of information I have. Ooh, 10 past 5 at night. Let's try it. Second order differential equation. To approach these, I have to make a substitution first. So let P equals dy dx. So now I get dp dx is equal to e to the minus x minus e to the x. Nice simple functions I've chosen here. Let's integrate. Now, because I've seen that my left-hand side always, when I integrate the left-hand side, I'm always going to get the whole amount, the whole thing. I'm not going to show the step of me integrating anymore. I'm just going to write down automatically that it's p on the left. Okay? So therefore we'll get the p variable on the left and the integral of e to the minus x minus e to the x and dx, being to split this up, multiply the dx to the other side, and we're going to integrate. So p gives us negative e to the x minus e to the x plus c, the first integration constant. Now let's figure out what this c is straight away. Okay? First thing I'm going to remember is that, well, I know what p is. P is actually dy dx. So that's what my first rule is. Dy dx is negative e to the negative x minus e to the x plus c. And if I check my little information I've got, this bit of information here is going to be helpful to help me figure out what my particular solution is for dy dx. It says when dy dx is equal to 0 when x is 0. So I'm going to sub in this information. X equals 0 and dy dx equals 0. So I'll have 0 equals negative e to the 0 minus e to the 0 plus c. Okay, e to the 0 is 1. So 0 equals minus 2 plus c, therefore c is equal to 2. That's good. Then dy dx is equal to negative e. Put it all together. We get that. So that's our first particular solution for dy dx. But we want to know what y is as a function of x. So we have to do it again, integrate it one more time, and use the next bit of additional information to find the particular solution for y. So now let's keep going. Y is then equal to the integral of the right hand side with respect to x, and that gives us, integrate each term, and now we've got e to the minus x minus e to the x plus 2x. Okay, the unit now becomes an x term, and I've got plus c, and the other integrating constant. Sure, I could call it d, but I've figured out what my previous c is. This is just another constant, so I'm just going to call it c for constant again. And there's my general solution for y now. I need to use my additional information to work out what is the particular solution for y. So sub in when x is equal to 0, y is equal to 0. So we'll go 0 equals e to the 0 minus e to the 0 plus 0 plus c. So therefore c is equal to, that is equal to 1, that is equal to 1, but now it's 1 minus 1. So c gives us 0. And finally, I've got my final answer. Y is equal to e to the negative x minus e to the x plus 2x. And the c's gone. It's gone to 0. What do you reckon? Interesting, yeah? Differential equations and finding solutions. It's not too much hard work, but we just break it down step by step. And we'll get there. Okay, so we're done. What I'd like you to do is please explore these exercises for homework. Okay, in class we're going to go right into exercise 9C. Okay, and we'll go from there. Thank you.